Picture this: 45-ton metal wings that wave like a gymnast's ribbon while carrying 500 people at 900 kilometers per hour. That jaw-dropping bend you see on an Airbus A380 isn't a flaw. It's the secret sauce that keeps the world's largest passenger jet aloft, efficient, and safe. In the next few minutes, we'll reveal how those rubber wings are engineered to flex over 4 meters without snapping, why that motion slashes fuel burn, and what it teaches us about the future of flight. If you geek out on aviation marvels, smash the like button, subscribe, and stay till the end. There's a myth-busting surprise waiting for you in the conclusion. Physics of wing flex. Imagine holding a long diving board at one end while someone stands on the other. The board sags, but thanks to a careful balance of stiffness and flexibility, it doesn't snap. An A380 wing works the same way, except the someone is 8 stories of lift force spread across nearly 80 meters. As air rushes over the aerofoil, pressure is lower on top and higher beneath, creating an upward bend called aeroelastic deflection. Engineers designed this cantilever to act like an enormous spring. Too stiff and it would crack under turbulence, too limp and it would flutter violently, a deadly phenomenon known as divergence. To keep that sweet spot, Airbus blended positive dihedral, an upward angle at the root, a tapered thickness ratio, and composite reinforced spars that grow sturdier toward the fuselage. The result? The tip can rise over 4 meters in cruise, spreading the load more evenly and slicing induced drag by roughly 3%, which translates straight into fuel savings. Design philosophy behind the A380 wing. How do you give the planet's biggest airliner a wing that's both airport-friendly and ocean-crossing efficient? Airbus started with a hard constraint. Under International Code F rules, the span had to stay below 80 meters, or the jet wouldn't fit existing gates. Engineers squeezed every centimeter, landing at 79.8 meters, but simply stretching a metal plank that wide would have been cripplingly heavy and draggy. Their solution was high aspect ratio plus smart taper. The route is thick, as wide as a city bus, stuffed with 250,000 liters of fuel, hydraulic lines, and a carbon fiber center spar that handles monstrous bending moments. From there, the chord narrows and the thickness thins, trimming weight while preserving structural depth where it matters most. Add 33 square meters curved sharklets, and you get just enough extra span to recapture lift lost to vortex drag without violating gate limits. The payoff: long-haul range to Los Angeles and Singapore with full payload, and wings that elegantly breathe under load. Materials and internal structure. If you could peel back the A380's painted skin, you'd find a high-tech skeleton worthy of a sci-fi set. The outer panels are lightweight aluminum lithium alloy, chosen for its crack resistance and heat tolerance. Underneath, 2 beefy carbon fiber reinforced plastic spars run span-wise like the jet's backbone, carrying most of the bending loads. Between them sit more than 120 rib sections, precision-milled vertebrae that shape the aerofoil and channel fuel, wiring, and ice protection ducts. To tame weight, Airbus replaced many traditional aluminum stringers with Glare, a glass fiber/aluminum laminate that absorbs impact energy yet weighs 10% less. In turbulent air, these layers flex minutely, diffusing stress the way laminated glass stops a crack from racing edge to edge. The synergy of metals and composites means the wing can bend dramatically without yielding, while still offering the forgiving damage tolerance inspectors love during heavy checks. Static load and certification testing. Before any A380 ever met a passenger, Airbus chained its prototype to a forest of hydraulic jacks inside a Toulouse hangar and began a slow-motion arm wrestle with physics. Regulations demand that wings survive 1.5 times their maximum design load, the so-called ultimate load, for at least 3 seconds. That meant ratcheting the wingtips upward nearly 8 meters, applying the equivalent of 7,000 tons of lift. At 145 times load on 1 November 2006, A rib feet bracket inside the left wing cracked, short of the target but still an engineering triumph. Airbus reinforced 2,000 brackets with titanium doublers, reran the test, and comfortably cleared certification. The episode proved two things. First, the structure still had generous safety margins even in failure. Second, the wing's built-in flexibility accurately signaled stress long before catastrophic breakage could occur. Benefits of all that flex. What do passengers actually gain from watching those wingtips dance? Plenty. First, a bending wing dampens turbulence. Every upward jolt transfers energy into structural flex instead of your coffee cup, trimming the sharp G-loads that cause air sickness. Second, the gradual arc spreads lift more evenly across the span, which cuts induced drag, saving roughly a ton of fuel on a typical 12-hour sector. Third, by absorbing gust energy, the structure suffers lower peak stresses, so Airbus could shave hundreds of kilos of metal without sacrificing fatigue life, weight that turns directly into extra payload or range. Finally, flex reduces hinge moment spikes on flaps and ailerons, extending component life and lowering maintenance bills. In short, smoother ride, cheaper tickets, greener skies. A 380 versus other big birds. If the A380's wing flex impresses you, check out Boeing's 787. Its carbon fiber tips can flap nearly 8 meters, giving the Dreamliner a surfer-like sway in light chop. Yet the Super Jumbo still outbends older metal giants such as the 747-400 and A340, whose stiffer aluminum spars yield barely 2 meters of travel. Why? Size and mission. The A380's enormous span generates higher bending moments, so engineers deliberately built in greater elasticity to keep stress within limits. Meanwhile, next-gen twins rely on composites to achieve similar flexibility without the A380's weight penalty. The lesson: materials differ, but the physics push all long-range jets toward wings that flex rather than fight the air. Myths and passenger perception. Passengers often whisper, "If it's bending, it must be braking." In truth, the opposite is true. Flex is safety made visible. The wing's redundancy, multiple spars, fail-safe ribs, load-shedding composites, keeps cracks contained and gives pilots warning. Fatigue tests drove the structure through 160,000 simulated flights, double any A380's planned life. So next time you watch that graceful arc, relax. The jet is doing what it was built to do. Looking ahead, morphing and folding wings. Airbus engineers aren't resting. Their Albatross 1 demonstrator tests semi-aero-elastic hinges that let wingtips fold during gusts, further cutting structural weight. Across the Atlantic, Boeing's transonic truss-braced wing concept explores even longer, ultra-slender spans braced by lightweight struts. Both ideas promise double-digit fuel savings, nudging aviation toward net zero emissions. The takeaway: tomorrow's wings will flex even more, and perhaps move on command. From airport gate to stratosphere, the A380's dramatic wing bend proves that flexibility equals strength, efficiency, and comfort. If this deep dive boosted your aviation IQ, smash like, hit subscribe, and share it so others can marvel too. Stay tuned. Our next episode busts the biggest supersonic comeback myths